How do you determine bond angles of a molecule? So this one can be a little bit tricky. Bond angles depend on two things: the amount of bonds it has. So bond angle, it depends on amount of bonds and amount of lone pairs. So we're actually going to create a table here. We're going to break down each one, but I want to make sure I have enough space, so let me just write it like this. So amount of bonds, you always have to start with a minimum of 2 bonds. So let me just put bonds here: 2, 3, 4, 5, 6, and yes, things do expand that much. And now amount of lone pairs. In fact, let me just move this down so that way up here I can put lone pairs. That's 2, 3, 4, 6, 0, 1. Sorry, might need more space than that. 0, 1, 2, 3, 4. I believe that's how far it goes for lone pairs. So let's start with, if it was something that had 2 bonds and 0 lone pairs, it would look like this. The element X, for example, just like that. It's called linear. An example of something like this, okay, would be like CaF2, okay, because calcium only has 2 electrons for it to give, and this is linear, and this angle is 180 degrees. Okay, so that is the first one. Now with this though, if it had 1 lone pair with well, I guess we can't really call them bonds. Think of it more of like the steric number, or things that is attached to. So not bonds, let's just call them attachments for now, something that's a little bit easier. Attachments. The reason why I'm saying it like that is because once you have 1 lone pair, for example, it'll kind of look like this, and this doesn't really have a, it doesn't have a degree because it's only one thing sticking out of it. That's like HF, for example, hydrogen fluoride. In fact, that's not even a good example because that one has a lot more. What would be a good example for this? Maybe like look at the periodic table. No, that wouldn't even work either, because most elements, if not all, like to be a certain way. So let's just actually cross this out, and this just wouldn't make sense either. So these ones don't exist. So let's move on to the third one then. So now we have 3 bonds, and it looks like this. Okay, and this, the angle is 120, and this right here would be like a BH3 or BF3. Actually, I've seen that one more. Boron with 3 fluorides attached to it, and the reason why boron is because boron has exactly 3 electrons it can attach, and fluoride just takes up those spaces. So with that, that's would be what it looks like. Now if we had 1 lone pair in this, it looks more like this. Okay, and this would actually be like would it be nitrogen? I think here, because these ones No, it'd be nice. It might have been like, most things would not even bond like this. I can't think off my head an example like that, but this angle here would be like less than 120. That's really all we can infer from that. And then, you know, you can't do more than that anymore. But the trend is usually that once you start including lone pairs, whatever the non-lone pairs is, you just know that it's something less. There's no specified number, just because it does vary, but just know that once you start adding lone pairs, because electrons like to exert a little bit more force in the whole shell, things kind of get pushed and get squeezed together if you're not an electron. So with that, let's move on to number 4. If we had 4 of them, this is what it would look like. Sorry. You kind of draw like this, because it kind of forms like a little tetrahedral, but this angle is 109 degrees. Okay, that's what 4 would look like. And a perfect example of this one, CH4, that's what that forms. Now with the lone pairs, if we had that, this would be what it would look like. X 2, 3, and actually we do have an example of this one finally. This would be like NH3, okay, because it has 5 electrons, so 3 of them can be paired, so that's 2 lone pairs. And this one, following the same rule, will be just a little bit less than 109 degrees, okay. And then now if we had 2 of them, oops, there we go, like that, this one is way, yep, I'm using the less sign, good, less than 109. We don't really know what it is. We assume that it's a lot less than 109. And actually a common example of this would actually be H2O. This is a perfect example of that, because oxygen has, you know, 6 electrons, so it shares 2 of them with 2 hydrogens, and then the other 4 form 2 lone pairs. So that's how we get that. Okay, and actually note that the most common, I guess, attachments that most elements have is 4. It usually doesn't like to go past that, which is why I couldn't come with an example of that lone pair here, like this one. This one is very rare in the natural world, as in I can't even think of anything that would bond like that willingly. So if there was 5 actually, so this one looks kind of like this, where you have that, and then you have the 3 chains kind of like circling this, forming a circle with each other like that. Okay, so then this right here would be a 90 degree, and these will be treated like the 120 degrees up there, and that's what we have there. As an example for this, let me just actually get rid of that. I don't like that. The X is better now. An example for this, something 5, honestly could not tell you, unfortunately, because exactly 4 is the most common one, but that would be the angles for it. And then, you know, if you added 1, you'd still have this, and you still have kind of like the ring there, okay, but the bottom would be where the electrons go. Now following that, this right here, this angle would be less than 90 degrees, and this angle will be less than 120. You see how the electrons just keep forcing things to be close to each other? That was what would happen there. And now with that, oh no, sorry, I drew this wrong. This is actually the most stable form. This would actually be more like this, so we'll still have these, and then these ones will be pushed aside. So exactly, so this angle here This is the one that's, you know, less than 90 degrees. And the angles between each other here, that's usually supposed to be 120, will be less than 120 degrees. So that's what would happen there. And once again, I cannot think of an example. And then it just kind of keeps going. So then now if we have two, it will form an actual like a T shape actually. It'll look like that. Okay. And these will surprisingly still be less than 90 degrees. So not exactly 90, just a little less than 90 degrees. And then after that, we have a pseudo linear again, surprisingly, because now this, and this is like one of the few examples, the rare ones, where actually it is 180 degrees. The electrons have now pushed both bonds to as far as they could away from each other, which is why we get back to that balanced 180. So that's what we get there. That's it for that one. Okay, so now we can talk about the last row, the sixth one. So this one is the one that's the most full, and I can actually think of an example. It would look like this. So everything is 90 degrees from each other. So in any angle, even here, down here, they're all 90 degrees from each other. That's as far as they can be comfortable. And I believe an example would be like something with sulfur. Sulfur can do the, or is it phosphorus? Something with, and maybe phosphorus can actually do the 5 and sulfur can do the 6. Strange stuff. But one of those, something. In fact, I'll write it here, I guess, for you to search up as well. Because right now we're focused on just angles. Something phosphorus, something sulfur. That's what I'm thinking here. And then we kind of, so this is where I made the mistake earlier. So this is the one where the the last electron would be under it, so like that. It'll kind of form like a star, but because the electron is pushing everything up, all these are going to be less than 9 degrees. Okay, and now if we had it, two of them, it'll kind of form a sandwich. So because it forms a sandwich, it kind of follows the same thing, to where instead of it being less than 90 degrees, the electrons have pushed everything as far away as possible, kind of like what happened here actually. So these ones are all actually back to being 90 degrees away from each other. And then if we had 3 of them, we're back to a pseudo bent shape. 2, 3, and then this sticks out. But this exactly is less than 90 degrees. Okay, these ones you don't really have to worry about them too much, and we're going to actually draw the last one. So the last one is also something that looks quote unquote linear. So it's kind of like this one again, where the electrons have pushed the bonds as far away from each other as possible, and is back to being 180 degrees. So these 3 here are the only examples, are the examples I can think of where you won't have to put that it's less than what it's supposed to be. Everything else, once you go past 0, in terms of once you go past 0 valence electrons, 0 lone pairs, then the angles start getting tighter and tighter and start squeezing together. So with that and everything said, this right here is how you determine bond angle. It's based on the amount of attachments they have, what amount of bonds they have, and it goes from 180 to 120, 109, and then 90. Okay, because that is the best shape it can put itself to comfortably fit all elements, well, I mean all molecules. So now, number 7. let's see. Yep, bent. So they actually give us a name for this one. I guess for number 6, they tell us that, for example, what we just did with the oxygen here, this less than 109 is called a bent. I guess molecular geometry. These are some of the things you may have to memorize along with their actual angle. So just keep that in mind, and I'm just gonna let you can pause it here if you want to write all these down. Okay. Oops. Oh no. Okay. Now let's move on to the next question.